before we start the third and last session of today's program and continue with the lectures of Professor.
Okay. Now, let's be back to curvature. How do we translate the basic meaning of curvature, definition, which was recalled at the beginning of the lectures, into something with which you can work, and in particular, compute distortions of volumes? So, curvature is about distortion of volumes. So Ricci curvature is about distortion of volumes along geodesics. Geodesics are contained in one single object, which is the exponential map. That is, if you give yourself a vector field V, by going along the geodesics generated by this vector field, you are going along the exponential map, and we want to know how this distorts the volumes. There is an infinitesimal way to distort the volumes, to compute the volume distortion. This is the Jacobian determinant. It is the infinitesimal version. So we need to compute the Jacobian determinant of the exponential map. This is a tricky computation, and we'll do it only in the case of V of x equals to grad psi of x for some function psi which goes from M to R. This case is enough to treat any situation of interest, in particular because it is a local computation, so all that matters really is the germ of the vector field at a given point, and you can always assume it is a gradient if it is symmetric, if the variation is symmetric, the first order variation of V. So here is the idea. This is x here, and I make small variations of x in all possible directions. So here this is an orthonormal basis, E1, etc., En, in the tangent space. And I take E1 to be the direction of grad psi, so normalized. And this gives me a certain geodesic, say gamma of t. Here, this here will be something like exponential x epsilon E1, epsilon E2, let's say, with epsilon very small, and epsilon will be like the size of the cube. So here I'm drawing the cube in the tangent space, but this will be a corresponding point. And then there will be a geodesics coming from here, which will be gamma 2 of t is exponential exponential starting from exponential x E1, epsilon E1, and this will be something like grad psi applied to exponential x E1, epsilon E1. And I put here a t. Okay. And the plan is what? To look at the Jacobian determinant of x t grad psi. And this is like the limit of the ratio of the volume of exponential t c epsilon. I write it here in a slightly fuzzy way, divided by the volume of c epsilon, where this here is a cube c epsilon. And this here, what you have is a kind of distorted version of the cube. Distorted because in some directions it is expanded, in some other directions maybe it is compressed. Anyway, you have the little cube, infinitesimal cube, and its image, and the infinitesimal ratio of the volumes as epsilon goes to 0 gives you the Jacobian determinant. It's the interpretation of Jacobian determinant as the infinitesimal ratio of the volumes. And so you want to compute this. And this goes into, as all problems in Riemannian geometry, differential equations in T. I will show you what the equations look like. So variations of geodesics are given by so-called Jacobi fields. These are vector-valued functions and the equation is simplified when you look at this in a moving frame. Moving frame meaning that you go along the geodesic and you change your frame of reference as you go along the geodesic, and you change it in a parallel way. It was discovered at the beginning of the 20th century that when you go along a certain path, you can make it in such a way that you always stay parallel to yourself. Staying parallel. So this is parallel transport. And so you have a basis which moves, and in this basis, you express the variation. So the basis changes at each time, and you look at the coefficients, and the equations will be of the form j double dot of t plus r of t, j of t equals 0. It's a second order linear differential equation. And this goes back to the old work of Jacobi. The matrix R of t here, let's say that if this is the matrix J1 of t, etc., Jn of t, corresponding to direction 1, etc., direction n, then R of t can be expressed in terms of the Riemann tensor at point gamma of t. And you apply it to gamma dot of t ei gamma dot of t ej. Well, and this is the coefficient ij of the matrix. So it's a matrix whose coefficients are computed using the Riemann tensor. And here is the equation. Okay. let's form u of t is, which one is it? J dot of t, j minus 1 of t. Yes. Then you see that u dot of t is equal to what? Minus plus j double dot j minus 1 minus j dot j minus 1 j dot j minus 1 by differentiating j minus 1. And this is the same as u square. And now j dot double dot j minus 1 through the equation is equal to minus r of t. So you obtain the equation u dot plus u square plus r equals 0. It's a matrix valued Riccati equation. And it's the fundamental basis of curvature in a way. Everything you want to read on curvature is in this equation to some extent. And then you manipulate. Important thing to know is that the trace of the matrix R is equal to the Ricci curvature applied in the direction gamma dot of t. So from this, we can establish differential equations. How to make the link with the Jacobian determinant? The Jacobian determinant is like the determinant of j of t. Then, if we differentiate the Jacobian determinant and look at the time differentiable time derivative of this, it will be determinant j of t multiplied by the trace of j minus 1 j dot. This is the formula about differentiating determinants. You multiply by you have determinant multiplied by the trace of the inverse of the matrix times the derivative of the matrix. But this is u. Well, it doesn't matter when I take the trace. I can always invert because trace of AB is equal to trace of BA. So this is equal to u. So it means, and this is equal to j, it means that I can relate the derivative of the Jacobian determinant to the trace of the matrix U. And so I will put here, and I will have relation between this Riccati equation and the evolution of the Jacobi determinant. And by putting this here, I will obtain inequalities about the Jacobian determinant in which Ricci curvature will be like an input term in this differential equation. This allows you to get the differential equations. So I will give you a result. So from this and the inequality trace of u square is bounded below by trace of u square divided by n, one can relate variations of j to the Ricci. And found that, for instance, Ricci non-negative in dimension n implies that j of t to the power 1 over n is concave as a function of t. So here we have this differential evolution of the Jacobian determinant depending on the Ricci curvature. Also, if no restriction on n, if we don't know what n is, we can always say that logarithm of j of t is concave as a function of t. Ricci non-negative, in general, implies this, whatever the dimension. The concavity, the log concavity of the Jacobian determinant of the exponential map along a gradient vector field. Let us also mention that there is a translation in terms of vector fields. Because what we did here is follow the exponential flow. But what if we how do you define the exponential flow? Well, I am here and my path. I look at the direction, I go forward, and I go as a geodesic. But now, this is in terms of trajectory, the geodesic. What if I want to think only about vector fields? Maybe I can find vector fields such that just going along the vector field at each time will give me the geodesic trajectories. It's an Eulerian point of view in the language of fluid mechanics. So how would we, starting from an initial grad psi of x, initial velocity field, can we modify this velocity field in such a way that particles following the flow will automatically be geodesic trajectories, have geodesic trajectories? And then you would like to have something like grad psi or v, depending on t and x, such that integral curves of these vector fields are geodesics. The answer is yes, we can do it. And v of tx should always be equal to grad psi of tx. And psi should evolve in time according to the so-called Hamilton-Jacobi equation, the simplest one, d psi dt plus grad psi square over 2 equals 0. This is Hamilton-Jacobi. And if you do this, instead of having trajectories, you will have a vector field changing in time. And everything we said, all the equations we wrote about trace of u, etc., you can rewrite them in terms of the vector fields and the time derivative of the vector field. Instead of looking at the time derivative of the Jacobian determinant, it will be a time derivative of the vector field. And if you do this, you will obtain another set of formulas. They look different, and when you look in Riemannian geometry textbooks, they are obtained in very different ways, but in fact they are just the same as the formulas with the Jacobian determinant. And they are called the Bochner formula, the variations of the Bochner formula. So it says for any smooth function psi from M to R, minus Laplace minus grad Laplace psi dot grad psi plus Laplace grad psi square over 2 is equal to the square of the norm of the Hessian of psi, Hilbert-Schmidt norm if you want. Now, if this was flat space, it would be equality, just this. But if it is non-flat, you need another term, and it is Ricci in the direction grad psi. This is the curvature term, arriving as a kind of nonlinear commutator, of first, second, and third order differential operators applied to psi. So that's another equivalent definition of Ricci curvature. And you notice that this is bounded below by Laplace psi square divided by n, capital N, the dimension, plus k times grad psi square if this is the infimum, a bound, lower bound on Ricci. Okay? This here, this inequality is called the CDKN inequality. And it's a functional way to encode the fact that the dimension has an upper bound n and a lower bound on the Ricci k. At the same time, they come together. It's impossible to separate them. C is for curvature, D is for dimension, CDKN. If you look at a large literature about Ricci curvature, it will start here. Many works by people like S.T. Yao, for instance, start with this, do a lot of integrations, estimates, etc., to prove deep results. This is the working heart of Ricci curvature theory. Sorry, here?
Second derivative, but you have the fourth derivative,
Oh, hold on, I did not understand the question.
I mean, left-hand side, there is fourth derivative. But which is second derivative?
Oh, left-hand side? No, there is only third derivatives. This is 2, this is 3. Oh, so here we have 3 derivatives. Here 1, here 2, here 1. Of course, there are the squares. Here it's only a first-order correction. All the second-order correction is here, and there is a first-order correction remaining, which is here. So this is Ricci. Okay, if you want, I write it explicitly because it's a quadratic form. So this, all these are quadratic terms. But this one is only a first-order derivative. So Ricci is a first-order correction in this, is a first-order correction in this. If you look here, the third-order term, they cancel out from here to here. And the second-order term, with these two, they cancel out. But there remains some first-order correction which has to be taken into account. This is Bochner formula. From this, derive many inequalities. With geometric significance. For instance, doubling property and the so-called Bishop-Gromov inequality. One particular case is that if you have CD 0n, then the volume of the ball of center x and radius r divided by r to the power n is a decreasing function of r. So the volume of the ball of radius r increases with R not faster than the volume of a ball in Euclidean space and dimension n. And this is called doubling property because it means that the ball of volume double will have a volume which is bounded by a constant times the volume of the ball of radius r. But also you have heat kernel estimates to show that the logarithm of the fundamental solution of the heat equation behaves like a square distance in some sense. But also Brun-Minkowski type inequalities. But also Sobolev inequalities. Sobolev inequalities in curve geometry, they involve constants which depend on Ricci curvature. But also isoperimetric inequalities, like the Levy-Gromov isoperimetric inequalities, which tell you that in positive curvature, the isoperimetric properties of your manifold are at least as good as the isoperimetric properties of a sphere with the same curvature, etc. So whenever you have an inequality involving Poincaré inequality is another example. Inequality involving measure and gradients, you can be sure that you need some estimate on the Ricci curvature. And in the proof, most often, one of these formulas will appear. Either the formula about the evolution of the Jacobian determinant or the Bochner formula, which will be used and integrated. And also, compactness of manifolds. Suppose that you want to work with geometry which can vary and you want to put a topology on all the possible geometries. And you want to know in which case I have compactness in my sequence of geometries. Then again, Ricci curvature bounds are the correct assumption. And there is this excellent, at the same time simple and deep theorem of Gromov. It is the Gromov's precompactness theorem. The space of compact Riemannian manifolds M such that dimension of M is bounded above by capital N, Ricci of M is bounded below by K, a real number, and diameter of M is bounded above by a certain number D, finite. And this is precompact in any topology. Natural notion is the measured Gromov-Hausdorff topology. Which is a topology in which you impose the convergence of measures of volume, say, and distances. And now you ask, if I take a sequence of geometries in this space, which is precompact, converging to something, what will it converge to? Maybe it's a manifold, but maybe not. Maybe it's a singular space. Can we describe it? And can we say that it is also CDKN in some sense? So the consequence of what I described, what I'm describing, is that yes, it is contained in the space of synthetic CD of Kn Ricci bounded spaces. In the sense that I define, so I just erase here, but in the sense that I defined with the entropy. How can we make the connection? Let me show it to you in a particular case. So how to describe the limit? Geometries. And for this, use the synthetic notion of CDKN. Because this is very robust under weak convergence. Let me explain. Let us see the link between curvature and optimal transport. So papers by Otto and myself, and papers by McCann, Cordero, and Schmuckenschläger. So let us see the link. Let mu t for t between 0 and 1 be a geodesic in the space of optimal transport. From general principles, one can show, I mean, it's true without curvature assumption, that mu t is obtained by looking at the intermediate map, exponential t grad psi, push forward mu 0, where mu 1 equals exponential grad psi, push forward mu 0, and this guy is optimal transport. So it says to look at the geodesic in the space of measures is easy. You take an optimal transport map from the first measure to the final measure, and you interpolate in between. To go from point 0 to point 1, you go along the geodesic. This is it. If I have the final point here, then I interpolate between time equals 0 to time equals 1. Okay. Let's write mu t to be equal to rho t times nu, where rho t is the density. Okay? And let's look at the function h. H nu of mu t is equal to integral rho t log rho t d nu. Okay? Well, this is the same as integral log rho t d mu t. Okay. Now, because I have the push forward here, I can write the Jacobian equation. And it will be like rho 0 of t, rho 0 of x equals rho 1 of T of x, Jacobian determinant of T of x. Well, this is in the sense of infinitesimal volume ratio. And similarly, rho 0 of x will be rho t of exponential t grad psi, Jacobian determinant of d exponential t grad psi. Let's make a change of variables. So this I put with a star, and I start again from here. Let's put this with a cross. Log rho t d mu t. And so I say that cross is the same as integral log rho t x t grad psi push forward mu t, push forward mu 0. And so I can change variables, and this will be the same as integral log rho t of exponential t grad psi multiplied by d mu 0 of x, integrated d mu 0 of x. But now I will use the formula star. Thanks to star, this will be the same as integral. So log of rho t of exponential t grad psi is here, the log of this. And I can express it with the log of this minus the log of this. Or like this. Log rho 0 of x divided by determinant d of exponential t grad psi. Mu 0 of dx. I use the property, additive property of the log. And I have the first term, which is integral log rho 0 of x mu 0 of dx. And then there is another term, which is minus integral log det d exponential t grad psi mu 0 of dx. What do we find here? It's the same thing we had before when we were studying the curvature. And I started by saying, look, in general, Ricci non-negative means that the logarithm of the Jacobian is concave as a function of t. So this is a concave function of t if Ricci is non-negative. This is fixed. And this is for any x. And here I integrate along the fixed measure. So this whole expression will be a convex function of t if Ricci is non-negative. And here we see the link. We see exactly the link, and we see that this property of concavity, log concavity of the Jacobian determinant, which was something infinitesimal, now is integrated into a global property, which is that this functional, which is an integral functional, be convex as a function of t along the geodesics of optimal transport. If I had tried to, for instance, prove some stability theorem using this, I would be lost because I need to prove to pass to the limit in the Jacobian determinant and so on. But now, no need. I just need to pass to the limit in inequalities which are integral. And this is very stable. very easy to pass through the limit. So that's the reason for the stability. And also, we see here the core of the reason for the equivalence. I'm not saying that here I have proven the equivalence between neutrino negative and this, but we've seen why it works. The key is this, the fact that we are integrated this concave function of t. So this leads to the synthetic definition, which I will rewrite here. So x d nu is said to satisfy CD of 0 infinity if for any mu 0 and any mu 1 there is a geodesic mu t geodesic path in the set of measures in let's say P2 of x, which is probability measures with distance equal the square root of the transport cost C2, optimal transport cost, such that h nu of mu t for any t in 0, 1 is bounded above by 1 minus th nu of mu 0 plus th nu of mu 1. So this is the definition that we introduced with Lott and Sturm almost 10 years ago. Yes, 10 years ago we started to introduce this definition, and it was the start of the theory with the idea, let us take this as definition and see to which point we can follow, to which point we can develop the theory. And so this definition, it was shown that it is stable under measured Gromov-Hausdorff topology. This means whenever you have weak convergence of the volume plus convergence of the distances, then you have convergence. In particular, this theorem gave the solution to a problem which seems very simple, but for which nowadays there is no other proof, which is if you have a sequence of Riemannian manifolds with non-negative Ricci curvature, and it converges in this sense to another Riemannian manifold, how do you prove that the limit has non-negative Ricci curvature? The problem seems so simple, but the only proof that we know to prove it, the only way we know to prove it, is to go through this definition with the information, with the entropies. So it's an example of a theorem that looks like a purely geometric problem, but that you solve using tools from optimization and statistical physics. So this definition is stable. This definition, this was the question that was asked at the first lecture, is compatible with the Cartan-Alexandrov-Toponogov bounds theory. This definition also allows to prove many inequalities. Sometimes under the extra assumption the extra geometric assumptions that geodesics are non-branching. Non-branching means that you can never have this, which means a geodesic separating into two geodesics. If you forbid this, it means your space is non-branching. For instance, Sobolev inequalities, isoperimetric inequalities, etc. In fact, all the list I gave, you can reprove these inequalities assuming only this. At a certain point, a few years ago, this was the situation. And you may ask also, is it more general? It is much more general than the smooth CD spaces. But for some people, it was too general. For instance, because it included, in particular, Banach spaces. Well, example, if you take any norm on Rn, and here you put a non-Euclidean norm, this is weak CDKN, CD0N. Okay, I did not mention here, but there are generalizations which I don't write here. To general CDKN, weak CDKN. So not only with zero infinity, by changing a bit the definition here and there, you can encode any k, any n. And then any space like this will be a weak CD0n space. Now, for some geometers, this was like heresy. And people like Petrunin said things like, if it is so general, then it is useless because it's too general. You don't want to have these. Why? In particular, because they don't satisfy the splitting property. Splitting property is something which looks like nice, but which to geometers is more than nice. It can be very important. Splitting property is if you have a space which has Ricci non-negative and an infinite line, an infinite geodesic, then it can be split along the geodesic. Let's say it's gamma. It can be split as gamma cross n. If you have an infinite line, you may split it. Split the space in the sense of Riemannian geometry as a scalar, also as a product, tensor product. But in general, if it is non-Euclidean, this norm here, you will not be able to write it in any way like the norm on the tensor product. And so, even though it has as many infinite lines as you want, so it doesn't satisfy the splitting property. So this suggested that there was room for a slightly more restricted notion of generalized. And it was developed by the. So this motivated the notion of weak RCD of Kn spaces with a slight reinforcement. Which is the reinforcement? The R is for Riemannian, and the reinforcement is for make sure that it is, in some sense, a Riemannian thing. So RCD means not only it is CD, Kn, plus the Sobolev space, the assumption that the Sobolev space W12, which means spaces whose first derivative is in L2, be a Hilbert space. Well, we learned this in functional analysis. When we take the first Sobolev space in L2, it has a Hilbert structure. But it's because we work with Euclidean norm. If we try to do the same on this, it will not be a Hilbert norm, a Hilbert space. And in general, on the metric space, this space will not be a Hilbert space. But if it is a Hilbert space, then it restricts a lot. If you think that this is a bit weird, let me tell you that it's equivalent to the assumption that the heat flow is linear. The two are exactly equivalent. If you are in a space in which the heat flow is linear and satisfies this curvature dimension assumption, then we'll say it is RCD. And now these RCD spaces, then they satisfy everything. They satisfy the splitting, and this was shown by Gilly. But they even satisfy some rectifiability property. And they satisfy a version of the Bochner formula, Bochner inequality, like almost everywhere. So then we really have the complete setting. On the one hand, if we want a slightly more restrictive context in which there is a splitting theorem and we have rectifiability and we don't have the Banach spaces but only spaces which are Riemannian in spirit, impose this condition. It still is stable under weak convergence and so on. But if you do want to include the very general spaces, then don't make this assumption, and you know that you will have access still to all inequalities. In particular, isoperimetric inequalities will work just the same for Banach spaces or for Hilbert-type spaces. For all these spaces, they will have this. All these spaces, they have the same isoperimetric inequalities, whatever norm you want, with same kind of shape of minimizer, same comparison principles. Doesn't matter whether it is Riemannian type or not. Only thing that matters is the curvature dimension condition, which is expressed in the synthetic way. It's also the only thing which matters to define a heat flow. Maybe linear, maybe nonlinear, but as soon as you have the curvature condition, you know it is uniquely defined. And with this, I conclude the 3 lectures. Thank you. Yes. Now it becomes a compactness theorem because it is closed. Unlike in the Gromov, it's really pre-compactness because the limit may not be a manifold. But now it is stable, so in fact it becomes a compactness theorem, absolutely.
And then the second question is then how, so basically I imagine that you start with spaces that you know and have some kind of smoothness in their sort of metrics, and then you converge to something, you want to conclude something about some sort of smoothness condition for that. And what are the type of techniques that you use there for showing that the final object belongs to the family of categories of
in fact, we don't. This was an option. This could have been an option, but we don't do it this way. One reason being that nobody knows how to do a good regularization of the notion of curvature. Curvature is a very non-linear condition in terms of the metric and so on. The metric gives a correspondence to something which is flat, but it's very nonlinear. And for instance, nobody has a good notion of how to regularize a non-smooth object of positive curvature while keeping the condition of positive curvature. And we actually don't know how to regularize this. It's still a big pain in the theory. So everything is done directly with non-smooth analysis. And from the start, you work with, and it's very typical in particular in the papers of the recent papers of the Italian school, full of non-smooth analysis in which you do directly all your things such as chain rule, such as going from one definition to another for the heat equation, non-smooth heat equation. Everything is done directly on a non-smooth space. And then when you do the convergence, it's stability from non-smooth to non-smooth. The only smoothness information which you show in the limit with this is some weak things such as rectifiability, using splitting, but using also the splitting is proven in non-smooth way. Actually, it was a motivation to replace all the classical proofs of these theorems, which did involve some smoothness, by proofs which involved no smoothness, and checking that they were very robust. So distributional Laplacian can be defined in this context, even with no smoothness, and so on and so forth. The Hamilton-Jacobi equation also. We use Hamilton-Jacobi equation in various parts of the proof, a non-smooth version of it, in which the semigroup is defined through this inf-convolution solution, which is known as the Hamilton-Jacobi-Bellman semigroup. And it is never used, the smoothness of the solution is never used.
So in the application you mentioned the assumption that the sort of limit is a priori a smooth solution.
We usually don't use it. When it comes from some completely different aspect of the problem, or in general, and it's a rare situation. In general, you don't know this.
Your point of departure was the definition of the Ricci curvature as the first correction term to the variation of the volume of longitude physics. Are the other correction terms interesting to study to the higher order?
Probably yes, but there's nothing which so far really comes in handy. Particular because this correction term, because it's a correction, is defined in a local way. But then it extends to a global definition with global consequences. And that's the strength of the notion of curvature, that you start from local, you arrive at global. And it's very rare. There are very few corrections which have this. For instance, think of this. When I look at this first variation, it gives me local information. But for instance, if the curvature is bounded below by a positive number, k, positive, and dimension is bounded above by some big number, then it is known that the diameter will be bounded. It's the Bonnet-Meyer theorem. And you know what will the bound be, something like square root of n minus 1 divided by k multiplied by constant. So you get global information from this local. And this is very rare. If we take any higher order correction, in general, there will not be any global translation of this. So there are, however, some exceptions which are some particular fourth order combinations. And in certain fields, they study these fourth order curvatures. It's related to some invariants, conformal invariants. People like Alice Chang in Princeton, Matt Gursky, Notre Dame, and others have studied some of these kind of higher order curvature. But again, still, these are very particular combinations. Here.
Thanks for your presentation, my question actually nothing done with the correlations. My question is about your lecture in the Royal Science Institute in London about the buffer tower.
About the
About the buffer tower in London, the Royal Science.
Oh, yes, Royal Institution.
2 weeks ago published on the YouTube. I want to know if we have some similarity with the complex system as a interdisciplinary science with the complex system. I want to know what's your opinion about complex system as mathematics.
Oh.
Second is what's the relation between your lecture today or all of the work you've done in Quantum Institute and the complex system?
Oh. So, complex systems is a rather loose term which is used to describe an area which involves a mixture of statistics, dynamical systems, and differential equations, often nonlinear, coupled together, and a set of tools and recipes to use this and consider this. We can say that with respect to the story that I have been telling here today, there are some points which make it a bit similar to complex systems and some points which make it quite different. The key word here is lower bound on Ricci curvature, say non-negative Ricci curvature. It's a typical indication for stability of observation. Ricci curvature bound tells that we'll always see things in a way which doesn't depart too much from the mean behavior, for instance. If we work with one of the big ideas behind the Ricci positive is the idea of concentration of measure. It means when I see the problem from a distance, it is as if the system occupies a finite volume, a very limited volume. It's concentrating in terms of the observation, maybe in large dimension. This is what is behind here in a sense. And this goes with the idea of stability. Complex systems usually are in the, let's say, philosophy of theory of chaos, which is at the same time the idea of unpredictability for trajectories individually, and this rather looks like negative curvature, but on the other hand, a good mixture property which makes it possible to investigate behavior on the mean, which may be the sign either of a well-mixing thing in negative curvature or a positive curvature, as in this case. So it's not completely stranger to some of the properties behind complex systems, but it also has very distinct characteristics. Here I gave an answer from point of view of the mathematical properties.
I'd like to ask about the notion you mentioned in the second talk about the large initial theory. Does it come to the computation of the mass transportation math?
Oh. There is an indirect link. There is yes and no. On the first hand, it appears that these are independent problems, the computation of the optimal map and the large deviation theory. But on other thoughts, the problem of the large deviation theory occurs to explain some of the properties in optimal transport. And in two ways. It can be seen in two ways. One is the relation to the heat equation. And I told you, so in the Sanov theorem, there was a relation between the large deviation theory and the entropy. And when you look at the heat equation, as I explained, the heat equation you can recover from procedure, which is like gradient flow of the entropy in the space of measures. So the entropy will go up and up and up, and the distance is expressed in terms of the optimal transport. Now, if one may ask, when I look at the optimal transport, each time I am like minimizing the integral of rho log rho d nu plus the transport cost, which will be something like minimal integral distance xy square pi dx dy, and there is a rho here, and here pi is really between rho nu, let's say, and rho k nu and rho nu. If I have it at step k, I want to go to step k plus 1. Okay. So this procedure is extremely general. This gives you the heat equation all the time, even if it's non-smooth, even if it's any kind of thing. And you may ask why this is related to heat. And you can make an interpretation in terms of large deviation. There are two researchers who did this 2 years ago. I forgot their name right now. And the answer, while this appears, is a large deviation. And the answer, while this appears, now this is very interesting, it's always with the square, even if it is a non-Euclidean norm at the base space. And this is related to the central limit theorem. So the 2 here is like the 2 of central limit theorem, and the entropy here is like the entropy in the Sanov theorem. So there is a link with statistical physics. Not really the optimal map, but in the problem here of heat equation, the fact that this large deviation plays a role. Now, the other field in which the Sanov appears is when you compare the optimal transport to entropy. And here is it actually. So this, in fact, was my very first theorem in the field. With Felix Otto in our 99 paper. Otto and myself, what did we prove? If a space satisfies logarithmic Sobolev inequality, this is logarithmic Sobolev inequality with constant k, that is, for any probability measure mu, h nu of mu is bounded above by I nu of mu over 2k, with h nu of mu is integral rho log rho d nu, and I nu of mu is integral grad rho square divided by rho d nu. This is a so-called Fisher information, and it's very important in information theory. So if that thing is true, always, then also it satisfies the so-called Talleyrand inequality with constant k, which means that the transport cost from mu to nu This is the transport cost. Is bounded above by h nu of mu divided by k. If you know this, then you have this automatically. And it's interesting because this is an information of so-called isoperimetric type, it's called logarithmic isobrev inequality, and this is an information of concentration type. It shows that isoperimetric principles imply concentration. And there's a long story behind this. But anyway, we proved it under certain assumptions, and then people generalized it again. And the best proof known is proved by a guy named Goslan, is based on the Sanov theorem, interpreting both sides in terms of large deviation theory.
See, we don't have precise implication from the rate function to the map, to mass transportation.
No. It's only the form of the map never appears, and I don't see how it would help. It is the value of the transport which is related there, not the map itself, but the value of the transport cost. Then, of course, there may be some relation between the value of the transport cost to the transport, but usually it's very difficult to get.
Our last question.
What are maybe examples about elliptic measure spaces other than manifold singularity property? Is there any relation between this character and the topology? For example, first homology like in facts of adjustment theory.
And what?
The relationship, is there any relationship between this Ricci character and topology, like classical theory, for example, something that says which is positive, the first homology?
Yes. This is true also if Ricci is positive. The same theorem remains true if Ricci is positive, then the first homology is equal to 0. And it's the same, as soon as you have the Bochner inequality, you do the same proof. So in this RCD, which I mentioned, you have the same proof. Let's say that when you are in this case, then all the topological consequences which we are used to are also true, because they all derive from the Bochner inequality, the ones which are known. So the relation to the topology is the same. This gives possibilities, on the other hand, to get some information on more general topology, so more general regularity. In the case where you don't put the R, as I said, you have all kinds of Pimsleur type geometries, which are generalization of a norm space, non-Euclidean norm space. So these are really wider classes. If you put the R, then they are more general in that you may have singularities, conical singularities, maybe dense sets of singularities, things like this. And these things may occur as limits of smooth manifolds. So it is, in some sense, natural closure of the notions. It is not known if any of these CD spaces can be obtained as limit of manifolds. But let's say that it's a natural space to contain the limits of all the smooth manifolds. Of course, these limits, also the topological information will be stable in general with respect to this limit. An example of, okay, so in terms of topological information, there is not so much that one can say with the curvature. The main theorem remains the one that you quoted about the first, about the H1 group. And sometimes you can use it, combine it in other directions. So it's rather about giving more general settings in which this kind of reasoning applies. let's mention that also it is not sensitive to the topology in the sense that you can, for instance, change a little bit the definitions and adapt it to spaces which are not even continuous, with possibility some approximation of a smooth manifold, but maybe a discrete approximation. And then you may still have some combinatoric type arguments that will work and may translate into approximate topological arguments if you replace your discrete set by a continuous approximation, things like this. So the key word is more flexibility and generality to the topological theorems that you already know and use.
Okay, so let's plan for a speaker again.
Thank you.
Just remind you that tomorrow there will be another talk at Sharif University of Technology again, and the day after tomorrow there will be another talk at the University of Denmark again at 9.